Hello and welcome to Sparx Science for Sleep, where the wonders of the universe unfold like a soft, starry blanket, wrapping you in a gentle embrace. I'm so glad you're here, perhaps curled up in your favorite cozy spot, ready to let your mind drift into a peaceful journey. Tonight, we're going to explore a question that sparkles like a distant galaxy. How did atoms, the tiny building blocks of everything, come to be from nothing? Science, you see, is like a quiet friend, whispering stories of the cosmos, and tonight, it's inviting you to listen. Take a deep breath, let your shoulders soften, and feel the weight of the day slip away, like sand falling through an hourglass. If you're struggling to sleep, this journey will cradle you into rest, and if you're simply curious, you'll find a little spark of wonder to carry into your dreams. I'd love to know where you're listening from. Maybe drop a comment to share your corner of the night and what time it is there. Now, settle in, close your eyes if you like, and let's begin. Imagine yourself floating in a vast, velvety void, where the stars are like tiny lanterns flickering in the distance, each one a story waiting to be told. This is the universe before it began, a place of infinite quiet, where time and space haven't yet found their rhythm. Science tells us that everything we know, every mountain, every breath, every heartbeat, started with a single moment, a cosmic spark called the Big Bang. Picture it not as a loud explosion, but as a gentle pulse, like the first note of a lullaby that set the universe humming. About 13.8 billion years ago, all the energy and matter that would become stars, planets, and even you were gathered into a point smaller than a grain of sand. It's hard to imagine, isn't it? A whole universe tucked into something so small, like a seed holding the promise of a forest. Let your mind rest on that thought, and feel yourself sinking deeper into calm, as if you're cradled by the cosmos itself. Now, let's linger in this quiet moment before creation, where the universe was a canvas of possibility. Scientists call this the singularity, a point where all the rules we know, time, space, gravity, were folded into a single, glowing mystery. It's not something we can fully grasp, like trying to hold a dream in your hands, but it's where our story begins. The Big Bang wasn't just a burst of light or heat, it was the universe taking its first breath, expanding outward in a soft, radiant wave. Imagine you're there, weightless, watching this tiny spark begin to glow, like a firefly waking up in the night. This moment wasn't chaotic, but serene, a delicate unfolding that would eventually weave the atoms that make up everything around us. As you breathe slowly, let your thoughts soften, and picture this cosmic beginning as a warm, glowing ember, inviting you to relax deeper still. The beauty of this story is how it connects us to something vast, yet so simple. The Big Bang was the universe's way of saying, "Let's begin," and from that whisper came the possibility of atoms, those tiny dancers that would one day form the oceans, the air, and even the thoughts drifting through your mind right now. Scientists have pieced this story together, like a puzzle, using telescopes to peer into the sky and particle accelerators to recreate the universe's earliest moments. It's like they're detectives, chasing clues left behind by the cosmos. But for now, you don't need to solve the puzzle. Just let it wash over you, like a gentle tide lapping at the shore. Feel your breath slow, your body soften, and let the wonder of this cosmic spark settle into your heart, as peaceful as a star twinkling in the night. As we rest in this moment, imagine the universe as a vast, quiet ocean, its waves just beginning to ripple outward. The Big Bang wasn't the end, but the start of a grand adventure, one that would lead to the creation of atoms, the building blocks of everything we cherish. You're part of that adventure, floating here in this calm, starry sea, where every question leads to a new discovery. Let your mind drift, as if carried by a soft current, and feel the universe's gentle pulse all around you. The story of atoms is a long one, and we're just at the beginning, but it's a story that invites you to relax, to wonder, and to let go. As you breathe deeply, let's glide forward, to a time when the universe began to cool, and the first whispers of particles started to dance in the cosmic dawn. Breathe gently now, letting the warmth of your cozy space wrap around you like a soft blanket. As we drift from the cosmic spark of the Big Bang, let's glide into a moment so brief, so delicate, it's like a single note held in the universe's first song. We're stepping into the Planck Epoch, a time when the universe was just a whisper, a fleeting instant at 10 to the power minus 43 seconds after its birth. This is a realm where everything we know, space, time, gravity, light, was woven into a single, glowing thread. Picture a quiet pond, its surface perfectly still, holding all possibilities in one serene moment. The Planck Epoch is like that pond, a place where the fundamental forces of nature danced as one before they began to find their separate rhythms. In this tiny sliver of time, the universe was unimaginably small, smaller than the tiniest speck you could imagine, yet brimming with infinite potential. Scientists call this the Planck scale, where the rules of physics as we know them blur into a kind of cosmic harmony. Gravity, electromagnetism, the strong force that holds atoms together, and the weak force that governs certain decays, they weren't distinct yet. They were like voices in a choir, singing a single note before breaking into their own melodies. Imagine a warm, golden glow, pulsing softly, as if the universe were taking its first, tentative breath. This was a moment of unity, a time when the cosmos was a single, shimmering possibility, waiting to unfold into the stars and galaxies we know today. The Planck Epoch is named after Max Planck, a scientist who, over a century ago, began to unravel the secrets of energy. He discovered that energy doesn't flow smoothly but comes in tiny packets, like droplets of water in a stream. These packets, called quanta, are so small they're measured by a number known as Planck's constant, a value so tiny it's almost a whisper of mathematics. During the Planck Epoch, this constant shaped the universe's earliest moments, setting the stage for everything to come. Picture a delicate web, each strand vibrating with the energy of creation, each quiver a promise of the particles that would one day form atoms. Scientists use this constant to understand the smallest scales of reality, where the universe was still deciding what it would become. Now, let's linger on the mystery of this epoch. The universe was so dense, so hot, that space and time themselves were tangled, like threads in a tightly wound ball of yarn. Scientists believe the temperature was beyond comprehension, reaching 10 to the power 32 degrees Kelvin. That's a number so vast it defies imagination, like counting every grain of sand on every beach in the world. Yet, in this intense heat, the four forces of nature, gravity, electromagnetism, the strong force, and the weak force were unified, acting as one. It's as if the universe was a single, perfect chord, resonating with the potential for all that exists. Imagine standing at the edge of a quiet lake, watching ripples spread outward, each one carrying a piece of the universe's first story. This unity wasn't something scientists could see directly, but they've pieced it together through mathematics and experiments, like detectives following clues left in the stars. They use theories like quantum gravity to explore this epoch, trying to understand how the forces work together before they split apart. It's like trying to hear the first note of a song that's been playing for billions of years. The Planck Epoch lasted only a fleeting moment, so short it's almost impossible to grasp, yet it was the foundation for everything. Picture a single drop of dew on a leaf, catching the first light of dawn, holding within it the reflection of an entire world. That's what this epoch was, a tiny, radiant beginning. One of the most fascinating ideas about the Planck Epoch is that it challenges our understanding of time itself. At this scale, time wasn't a steady river flowing forward, but a shimmering, uncertain thing, like light dancing on water. Scientists think that beyond this point, closer to the very start of the universe, our ideas of before and after start to blur. It's a humbling thought, isn't it? The universe, in its earliest moments, was a place where the rules we rely on hadn't yet taken shape. Imagine a soft, glowing mist, where every direction is the same, every moment eternal, yet ready to burst into motion. This is where the seeds of atoms were planted, even if they wouldn't bloom for eons. The forces that were unified in this epoch are the architects of our world. Gravity, which pulls stars together and keeps planets in orbit, was there, but it shared the stage with electromagnetism, the force behind light, and the bonds of atoms. The strong force, which glues protons and neutrons together, and the weak force, which helps stars shine by allowing particles to change, were part of this cosmic unity. Picture them as colors in a painter's palette, blended together before they're brushed onto the canvas of the universe. Scientists believe that as the Planck Epoch ended, these forces began to separate, like dancers stepping out of a circle to begin their own routines. This separation was the first step toward creating the particles that would form atoms. To explore this epoch, scientists used tools like particle accelerators, massive machines that recreate the high-energy conditions of the early universe. These accelerators, like the ones at CERN, smash particles together to glimpse the forces at play in those first moments. It's as if they're turning back the clock, listening to the echoes of that cosmic chord. Imagine a quiet laboratory filled with the hum of machines where scientists are chasing the secrets of creation. Their work helps us understand how the universe moved from a single, unified force to the diverse forces that shape our world today. It's a slow, patient process, like piecing together a mosaic from fragments scattered across time. The Planck epoch also raises a profound question. What was before? Scientists aren't sure, and that's part of the beauty of this story. The singularity, that tiny point before the Big Bang, is like a door we can't open, a mystery that invites wonder. Some theories suggest a quantum foam, a bubbling sea of possibilities where universes might form and fade. Others propose that time itself began with the Big Bang, making before a question without an answer. Picture a book with its first page missing, yet the story it tells is still breathtaking. The Planck epoch is the first word we can read, a word that holds the promise of stars, planets, and life. As the Planck epoch drew to a close, the universe was ready to expand, to stretch its boundaries, and begin shaping the particles that would become atoms. This transition was subtle, like the moment a seed begins to sprout beneath the soil. The forces, once united, started to find their own paths, setting the stage for the next chapter of the cosmic story. Scientists call this the Grand Unification Epoch, where gravity began to stand apart, leaving the other forces to weave their own patterns. Imagine a tapestry slowly unfolding, its threads separating to reveal a new design. The universe was cooling, ever so slightly, preparing to welcome the first particles into its embrace. The Planck epoch, though brief, was a moment of infinite possibility, where the universe held its breath before leaping into existence. Scientists use the term Planck time to describe this fleeting instant, a time so short it's measured in fractions of a second too small to imagine. Yet, in that fraction, the groundwork for everything was laid. Picture a single spark in a dark night, tiny but powerful, lighting the way for a grand fireworks display. That spark was the Planck epoch, and its glow still echoes in the atoms that make up the world around us. The universe was finding its voice, ready to sing a song that would echo for billions of years. This epoch also reminds us how science is a journey of curiosity, a quest to understand the universe's earliest moments. Scientists don't have all the answers, but they keep asking questions, building theories like bridges to the unknown. They use mathematics to describe the Planck epoch, equations that dance like poetry, revealing patterns in the chaos. Imagine a quiet study, filled with scribbled notes and glowing screens, where minds work together to unravel the universe's secrets. Their efforts bring us closer to understanding how the forces of nature came together, then parted, to create the building blocks of atoms. As we linger in this moment, the Planck epoch feels like a gentle pause, a breath before the universe's grand performance. The forces, unified for just an instant, were like a family gathered around a hearth, sharing warmth before stepping out into the world. This unity is a reminder that everything in the universe, every star, every tree, every breath you take, shares a common origin. The atoms that would one day form your world were born from this cosmic harmony, a harmony that still resonates in the laws of physics. Picture a soft golden light, spreading outward, carrying the promise of creation. The Planck epoch also introduces us to the idea of quantum gravity, a field where scientists try to blend the rules of the very large, like gravity, with the rules of the very small, like quantum mechanics. It's like trying to teach two different languages to speak to each other, finding a common tongue for the cosmos. In this epoch, these rules were one, but as the universe grew, they diverged, shaping the world we see today. Imagine two rivers merging into one, then splitting again, each carrying its own current, but forever linked. This blending of forces set the stage for the particles that would become atoms, a story that's still unfolding. Now, As the Planck epoch fades, the universe is ready to stretch its wings, to expand into something new. The forces are beginning to separate, like notes in a melody finding their own pitch. The cosmos is cooling, its energy softening, preparing to weave the first particles into existence. Scientists tell us this is where the story of atoms truly begins, as the universe moves from unity to diversity, from a single note to a symphony. Picture a quiet dawn, where the first rays of light touch the Earth, promising a new day. That's where we're headed next, to a time when the universe expands, and the first particles start to dance in the cosmic light. Breathe softly now, letting the quiet of the night cradle you as we drift from the Planck Epoch's glowing unity. The universe, once a single shimmering note, is ready to stretch its wings, unfolding into a vast, radiant canvas. We're entering a moment called cosmic inflation, a brief yet breathtaking chapter that happened between 10 to the power minus 36 and 10 to the power minus 33 seconds after the Big Bang. In this fleeting instant, the universe expanded faster than a heartbeat, growing from a speck smaller than a grain of dust to something the size of a ripe orange. Picture a tiny bubble of light, swelling gently, like a flower opening its petals to the morning sun, creating space for the stars and atoms to come. This rapid expansion wasn't like anything we see in our everyday world. It was space itself stretching, pulling distant points apart at speeds faster than light. Scientists tell us this doesn't break the rules of physics, because it's not objects moving through space, but space growing, like dough rising in a warm oven. Imagine a soft, glowing fabric, its threads spreading outward, making room for the universe's grand design. During inflation, the cosmos smoothed out, erasing tiny imperfections, much like a lake settling into stillness after a pebble's ripple fades. This smoothing created a uniform stage, a vast playground where the first particles could begin to form, setting the path for atoms to emerge. The energy driving this expansion is a mystery, a force scientists call the inflaton field. It's like an invisible wind, pushing the universe to grow in a cosmic blink. Picture a gentle breeze stirring a field of golden wheat, each stalk swaying as the universe took its first bold step. This field carried immense energy, so powerful it stretched the cosmos in an instant, transforming a pinpoint into a vast expanse. Scientists believe this energy came from quantum fluctuations, tiny ripples in the fabric of reality, like whispers in a quiet room. These ripples, stretched by inflation, became the seeds of galaxies, the blueprints for the universe's structure, guiding where stars and planets would one day shine. Inflation was so swift, so delicate, it lasted only a fraction of a second, yet it changed everything. The universe grew by a factor of 10 to the power 26, an expansion so vast it's like a single drop of water becoming an ocean. Imagine a tiny spark of light, blooming into a radiant sphere, its glow reaching across unimaginable distances. This growth made the universe flat and smooth, a perfect canvas for creation. Scientists discovered this through observations of the cosmic microwave background, a faint glow that carries echoes of the early universe, like a distant memory etched in starlight. Their telescopes, peering into the sky, found patterns that matched the predictions of inflation, confirming its role in shaping our world. The beauty of inflation lies in how it prepared the universe for atoms. By stretching space, it cooled the cosmos, lowering the searing temperatures of the Planck Epoch. Picture a glowing ember cooling in the night air, its heat softening as it settles into a gentle warmth. This cooling allowed the forces of nature to continue their separation, with gravity standing apart while the other forces, electromagnetism, the strong force, and the weak force, began to find their own paths. It was as if the universe was unfolding a map, each line marking a step toward the particles that would form atoms, the building blocks of everything we know. Scientists study inflation through complex models, piecing together clues from the universe's earliest light. They use mathematics to describe how the inflaton field drove this expansion, like artists sketching the outline of a masterpiece. Imagine a quiet room filled with equations, each one a brushstroke painting the story of the cosmos. These models suggest that inflation didn't just make the universe bigger, it made it possible for matter to exist. Without this rapid stretch, the cosmos might have stayed too dense, too chaotic, for particles to form. Instead, Inflation gave the universe room to breathe, a vast stage for the dance of creation to begin. One of the most intriguing ideas about inflation is that it erased almost all traces of what came before. It's like a tide washing over a sandy shore, smoothing away footprints to leave a pristine beach. This makes it hard for scientists to know exactly what sparked the Big Bang, or what existed before inflation. Some think the inflaton field was like a cosmic spring, releasing stored energy to push the universe outward. Others wonder if our universe is just one bubble in a vast sea of other universes, each born from its own moment of inflation. Picture a field of glowing bubbles, each one a universe, floating in an endless cosmic mist, each with its own story to tell. The patterns left by inflation are still visible today, etched in the cosmic microwave background. Scientists use giant telescopes, perched on mountaintops or floating in space, to study this faint glow, like reading an ancient manuscript written in light. These patterns show tiny variations, like ripples on a pond, that grew into the galaxies and stars we see today. Imagine tracing your finger across a starry sky, feeling the echoes of inflation's gentle push. These observations, made with tools like the Planck satellite, have helped scientists confirm that inflation happened, giving us a glimpse into the universe's first expansion, a moment that paved the way for atoms to form. During inflation, the universe's energy was transformed, setting the stage for particles to emerge. The inflaton field, once it had done its work, began to fade, its energy converting into the first particles, like a river flowing into a new channel. Picture a glowing stream, its waters turning into tiny sparks that would become quarks and electrons, the ingredients of atoms. This transformation wasn't sudden but gradual, like dawn creeping over a horizon, bringing light to a sleeping world. Scientists believe this energy shift marked the end of inflation as the universe settled into a new phase, ready to welcome the first building blocks of matter. The speed of inflation is hard to fathom. In less than a blink, the universe grew by a factor so large it dwarfs the distance between stars. Yet, this wasn't a chaotic rush, but a graceful unfolding, like a dancer spinning across a stage. The cosmos expanded smoothly, creating a uniform backdrop where particles could form without being crushed by density or heat. Imagine a vast, open meadow, its grasses swaying in a gentle breeze, offering space for life to take root. This smoothness is why the universe looks so similar in every direction, a balance that allowed atoms to eventually form stars and galaxies, creating the world we know. Inflation also solved a puzzle scientists call the flatness problem. Without inflation, the universe might have curved too much, collapsing back on itself or spreading too thin. Instead, inflation stretched it just right, like a sheet pulled taut across a bed. Picture a perfectly balanced scale, holding the cosmos in equilibrium. This balance is why the universe could grow large enough for galaxies to form, each one a collection of atoms born from this early expansion. Scientists discovered this by studying the geometry of the universe, using light from distant stars to measure its shape, like surveyors mapping a vast, unseen land. Another mystery of inflation is how it set the stage for the universe's structure. Those tiny quantum fluctuations, stretched by inflation, became the seeds of galaxies. Imagine planting a garden, each seed destined to grow into a towering tree. These fluctuations were like whispers in the early universe, amplified by inflation to create the cosmic landscapes we see today. Scientists study these patterns in the cosmic microwave background, finding clues to how inflation shaped the universe's growth. Their work is like listening to a distant song, each note revealing a piece of the cosmos's history, guiding us toward the story of atoms. As inflation ended, the universe was no longer a tiny speck, but a vast, cooling expanse, ready for the next chapter. The energy of the inflaton field transformed into particles, like a painter dipping a brush into new colors. This moment marked the beginning of the Quark Epoch, where the first tiny sparks of matter would start to take shape. Picture a quiet forest after a rain, its air fresh and full of possibility, ready for new life to emerge. The universe was cooling, its energy softening, preparing to weave the first particles into the tapestry of existence, a tapestry that would one day include the atoms that make up everything. The legacy of inflation is all around us, in the stars, the planets, and the very air we breathe. Scientists believe that without this rapid expansion, the universe might have been too dense for atoms to form or too uneven for galaxies to take shape. Imagine a world where the sky is empty, no stars to light the night, no planets to call home. Inflation gave the universe the space it needed, like a stage set for a grand performance. As we drift through this story, the cosmos feels vast yet gentle, a place where every particle has a role, every moment a purpose, leading us closer to the atoms that form our world. Now, as the universe settles into its new size, it's ready to welcome the first particles, the tiny sparks that will become quarks and electrons. The cosmos is cooling, its energy softening, like a fire settling into glowing embers. This is where the story of atoms continues, in a time called the Quark Epoch, where the universe begins to weave its first threads of matter. Picture a quiet dawn, the sky just beginning to glow as the cosmos prepares to bring its particles to life. Let's drift gently into this next chapter, where the universe's story unfolds further, and the first pieces of atoms start to dance in the cosmic light. Let your breath flow softly now, easing you into a gentle calm as we drift from the universe's grand expansion during inflation. The cosmos, once a tiny bubble stretched wide, is now cooling, its fiery glow softening like a sunset fading into twilight. We're entering the Quark Epoch, a fleeting moment around 10 to the power minus 11 seconds after the Big Bang, when the universe began to weave its first tiny sparks of matter. This is the time when quarks, electrons, and other fundamental particles started to take shape, dancing into existence like fireflies flickering in a warm summer night. Picture a vast glowing mist, where the seeds of atoms first stirred, ready to become the building blocks of everything we know. In this epoch, the universe was still a scorching sea of energy, with temperatures soaring to a quadrillion degrees Kelvin, hot enough to melt any notion of solid matter. Quarks, those minuscule bits of reality, were born in this fiery cradle, zipping through the cosmos like tiny embers. These quarks are the smallest ingredients of protons and neutrons, the pieces that would later form the hearts of atoms. Scientists tell us that quarks are held together by a force called the strong force, carried by particles called gluons, which act like invisible threads, tying quarks into tight knots. Imagine a cosmic tapestry, its fibers shimmering as quarks begin to find their partners, preparing to create the first stable particles. The Quark Epoch was a time of transformation, when the universe's energy began to condense into matter. One of the key players in this moment was the Higgs field, a kind of cosmic ocean that gives particles their mass. Without the Higgs field, quarks and electrons would be weightless, flitting about like ghosts, unable to form the atoms we know. Picture a gentle current flowing through the universe, touching each particle with a whisper of weight, grounding them in reality. Scientists discovered the Higgs field through experiments at places like CERN, where they smashed particles together to catch glimpses of this invisible force, like finding a hidden melody in a vast orchestra. During this epoch, the universe was a bustling soup of particles, with quarks, electrons, and their opposites antiquarks and positrons swirling in a chaotic dance. These antiparticles are like mirror images, carrying opposite charges, and when they meet their counterparts, they vanish in a burst of light. Imagine two raindrops colliding on a window pane, merging into a flash of brilliance before disappearing. This was a time when the universe was still finding its balance, with matter and antimatter locked in a delicate struggle. Scientists believe that a tiny imbalance, a slight preference for matter, allowed some quarks and electrons to survive, setting the stage for atoms to form later. The Quark Epoch also saw a crucial event called electroweak symmetry breaking, where the forces of electromagnetism and the weak force, which governs certain particle decays, parted ways. Before this moment, these forces were blended, like colors mixed on a painter's palette. As the universe cooled, they separated, each taking on its own role in shaping the cosmos. Picture a prism splitting a beam of light into a rainbow, each color finding its own path. This separation allowed quarks and electrons to take on their distinct properties, like actors stepping into their roles on a cosmic stage. Scientists study this process through particle accelerators, recreating the high-energy conditions of the early universe to understand how these forces shaped matter. Quarks come in different types, or flavors, like up and down quarks, which are the building blocks of protons and neutrons. A proton, for instance, is made of two up quarks and one down quark, held together by gluons, while a neutron has two down quarks and one up quark. Imagine a tiny recipe where quarks are ingredients mixed in just the right way to create something new. These combinations were just beginning to form in the Quark Epoch, as the universe cooled enough for the strong force to bind quarks together. Scientists used the standard model of particle physics, a kind of cosmic cookbook, to describe how these particles interact, revealing the rules that govern the universe's smallest pieces. The Higgs field played a starring role in this epoch, giving particles mass through a process that's both simple and profound. When particles move through the Higgs field, it's like wading through a gentle stream. The field slows them down, giving them weight. Without this, the universe would be a very different place, with no atoms, no stars, no life. Imagine a world where everything is light as air, floating without substance, unable to hold together. Scientists confirmed the Higgs field's existence in 2012, when they detected the Higgs boson, a particle like a ripple in the field, using massive machines that probe the secrets of the cosmos, like explorers charting an unseen land. The Quark Epoch was also a time when the universe was filled with a plasma, a hot, dense mix of particles and energy. This plasma was too chaotic for quarks to settle into stable forms, like a stormy sea tossing ships before they can find harbor. As the universe cooled, this plasma began to calm, allowing quarks to pair up and form the beginnings of protons and neutrons. Picture a turbulent river slowing into a gentle stream, its waters clearing to reveal the pebbles beneath. This cooling was critical, as it set the stage for the next step in the universe's journey, when these particles would combine into the building blocks of atoms. Scientists learn about the Quark Epoch by studying the universe's earliest light, captured in the cosmic microwave background, and by recreating its conditions in laboratories. These experiments are like time machines, letting us peek into the universe's infancy. Imagine a scientist in a quiet lab, surrounded by humming machines, chasing the echoes of those first moments when quarks began to form. Their work helps us understand how the universe transitioned from a sea of energy to a place where matter could take shape, laying the groundwork for the atoms that would one day form stars, planets, and life. Another fascinating aspect of this epoch is the role of neutrinos, tiny particles that barely interact with anything else. In the Quark Epoch, neutrinos were everywhere, zipping through the cosmic soup like silent messengers. They're so elusive that trillions pass through you every second, unnoticed, like whispers you can't quite hear. Scientists study neutrinos using massive detectors buried deep underground, catching these ghostly particles to learn about the early universe. Picture a vast, quiet cave where machines listen for the faint hum of neutrinos, each one carrying a story from the Quark Epoch, a clue to how matter began to form. The slight imbalance between matter and antimatter in this epoch is one of the universe's great mysteries. If matter and antimatter had been perfectly balanced, they would have annihilated each other, leaving nothing but light. Instead, a tiny excess of matter survived, like a single seed taking root in a vast field. Scientists call this asymmetry baryogenesis, and they're still searching for its cause, using experiments and theories to unravel why our universe favors matter. Imagine a delicate balance, tipped just enough to let a few quarks and electrons endure, ensuring the universe could one day be filled with atoms. As the Quark Epoch unfolded, the universe was still a place of incredible energy, with particles colliding and transforming in a cosmic ballet. The strong force, carried by gluons, was like a choreographer, guiding quarks into their roles. Picture a dance floor where each step is precise, each movement purposeful, as quarks begin to form the first stable particles. This was a time when the universe was finding its rhythm, cooling just enough for the chaos to settle, allowing the seeds of atoms to take root. Scientists use quantum chromodynamics, a field of physics, to describe how the strong force works, painting a picture of a universe knitting itself together. The Quark Epoch lasted only a brief moment, until about 10 to the power -6 seconds after the Big Bang, when the universe cooled further, allowing quarks to combine into protons and neutrons. This transition was like a curtain falling on one act of a play, revealing the next. The cosmos was ready to move from a sea of free quarks to a place where stable particles could form, the first steps toward atoms. Imagine a sky clearing after a storm, revealing the first stars twinkling in the distance, each one a promise of what's to come. This cooling set the stage for the next epoch, where the universe would begin to build the foundations of matter. The particles born in this epoch are the ancestors of every atom in the universe, from the hydrogen in a star to the oxygen in your breath. Scientists study these particles using theories like the Standard Model, which describes how quarks, electrons, and forces interact. It's like a map of the cosmos's smallest pieces, showing how they fit together to create everything we see. Picture a puzzle slowly coming together, each piece a quark or electron, forming a picture of the universe's earliest moments. These particles, born in the Quark Epoch, carried the potential for all that would follow, from galaxies to life itself. As the Quark Epoch drew to a close, the universe was ready for its next chapter, a time when quarks would combine into protons and neutrons, the building blocks of atomic nuclei. The cosmos was cooling, its energy softening, like a fire settling into glowing coals. This is where the story of atoms continues, in the Hadron Epoch, where the first stable particles begin to form, setting the stage for the atoms that would one day shape the universe. Picture a quiet meadow where the first flowers begin to bloom, each one a promise of a vibrant garden. Let's drift gently into this next chapter, where the universe weaves its first threads of matter, bringing us closer to the atoms that make up our world. Let your breath ease into a gentle rhythm now, as we slip away from the Quark Epoch's shimmering mist, where tiny sparks of quarks and electrons began their cosmic dance. The universe, cooling like a glowing ember settling into a soft warmth, is ready to take its next step. We're entering the Hadron Epoch, a fleeting moment around 10 to the power minus 5 seconds after the Big Bang, when the chaotic swirl of quarks began to find partners, forming the first protons and neutrons. Picture a cosmic kitchen, its air filled with the hum of creation, where ingredients blend slowly, like dough rising under a baker's careful hands, shaping the building blocks of atoms that would one day form stars and worlds. In this epoch, the universe was still a fiery sea, but its temperature had dropped to about 1 trillion degrees Kelvin, cool enough for quarks to come together. Quarks, those tiny flecks of matter, were once free, zipping through the cosmos like fireflies in a storm. Now, as the universe cooled, the strong force, carried by gluons, began to bind them into stable groups of 3, creating protons and neutrons. A proton, for instance, is 2 up quarks and 1 down quark, while a neutron is 2 down quarks and 1 up quark, each held together like pearls strung on an invisible thread. Imagine a delicate necklace forming in the cosmic glow, each bead a quark, clicking into place to create something new and lasting. This transformation from a quark plasma to a hadron gas was a pivotal moment, like a river calming after a turbulent rush, revealing clear waters beneath. The strong force, far more powerful than the electromagnetic force that would later hold atoms together, acted like a cosmic glue, pulling quarks into tight knots. Scientists call these bound quarks hadrons, a family that includes protons and neutrons, the sturdy cores of future atoms. Picture a bustling marketplace where quarks trade their freedom for stability, grouping together to form particles that would endure for billions of years, carrying the promise of galaxies and life. One of the most intriguing aspects of the Hadron Epoch is the subtle asymmetry between matter and antimatter. In the Quark Epoch, matter and antimatter particles were nearly equal, colliding and vanishing in bursts of light. But a tiny imbalance, a whisper of difference, allowed more matter to survive. This asymmetry, called baryogenesis, ensured that some quarks and electrons persisted, while their antimatter counterparts faded. Imagine a delicate scale just barely tipping to one side, preserving a handful of quarks to form protons and neutrons. Scientists are still unraveling this mystery, using experiments to probe why the universe favored matter, a question that echoes through the cosmos like a distant song. The Hadron Epoch also saw the creation of other particles, like mesons, which are made of a quark and an antiquark. These fleeting particles, unlike protons and neutrons, quickly decay, transforming into photons or other forms of energy. Picture a cosmic fireworks display where mesons sparkle briefly before fading, leaving protons and neutrons as the enduring stars of the show. Scientists study these decays in particle accelerators, smashing particles together to recreate the conditions of the early universe. These machines, humming with energy, act like time machines, letting us glimpse the moment when hadrons first formed, setting the stage for atoms to come. Protons and neutrons born in this epoch are remarkably stable, especially protons, which can last for billions of years without breaking down. This stability is crucial, as it allowed these particles to survive long enough to form the nuclei of atoms. Imagine a sturdy foundation, laid brick by brick, ready to support the vast structure of the universe. Scientists believe protons might eventually decay, but their half-life is so long 10 to the power 34 years that they're practically eternal. This durability, forged in the Hadron Epoch, ensured that the universe could build atoms, stars, and planets, creating the world we know. The strong force, which binds quarks into hadrons, works over incredibly short distances, about the size of a proton. Beyond this range, its power fades quickly, like a candle's light dimming in a large room. This limited reach is why protons and neutrons could form without being overwhelmed by the chaos of the early universe. Picture a cozy circle of friends, holding hands tightly, unaffected by the bustling crowd beyond. Scientists use quantum chromodynamics to study this force, describing how gluons carry a kind of charge, called color, that binds quarks together, ensuring the stability of protons and neutrons. During the Hadron Epoch, the universe was still a dense, hot place, but it was cooling rapidly, like a summer day giving way to a cool evening breeze. This cooling allowed quarks to settle into their new roles, forming hadrons that would become the hearts of atoms. The transition from a quark plasma to a hadron gas was like a symphony finding its melody, with each note a particle taking shape. Scientists recreate these conditions in laboratories, using massive accelerators to smash particles together, revealing how quarks and gluons interacted in those early moments, like historians piecing together an ancient tale. Another key player in this epoch was the weak force, which governs certain particle transformations. Unlike the strong force, the weak force can change one type of quark into another, like a painter switching colors on a canvas. This force played a role in balancing the numbers of protons and neutrons, ensuring the universe had the right mix for atoms to form later. Imagine a cosmic artist carefully blending hues to create a balanced picture, each stroke a quark, transforming to keep the universe in harmony. Scientists study the weak force through experiments that detect rare particle decays, shedding light on how the universe shaped its early matter. The Hadron Epoch also set the stage for a crucial cosmic ratio, about 7 protons for every neutron. This balance, determined by the slight mass difference between up and down quarks, shaped the universe's future. Protons, with 2 up quarks and 1 down quark, are slightly lighter than neutrons, which have 2 down quarks and 1 up quark. This difference, as small as a whisper, favored protons during the cooling process, ensuring there were enough to form hydrogen, the most abundant element in the universe. Picture a gentle tide, washing more shells onto one shore than another, shaping the landscape for eons to come. Scientists learn about the Hadron Epoch by studying the universe's oldest light, the cosmic microwave background, and by analyzing data from particle accelerators. These tools act like windows into the past, showing how protons and neutrons emerged from the quark plasma. Imagine a scientist peering through a telescope, not at stars, but at the faint glow of the universe's infancy, tracing the origins of matter. Their work reveals how the Hadron Epoch was a turning point, when the universe moved from a sea of free quarks to a place where stable particles could endure, paving the way for atoms. The asymmetry between matter and antimatter, cemented in this epoch, is one of the universe's greatest puzzles. Without this imbalance, the universe might have been left empty, filled only with light from matter-antimatter annihilation. Scientists explore this mystery through experiments like those at the Large Hadron Collider, searching for clues to why matter prevailed. Picture a detective sifting through ancient clues, each particle a hint to why the universe chose matter over its mirror image, allowing protons and neutrons to form the seeds of atoms. As the Hadron Epoch unfolded, The universe was filled with a gas of hadrons, protons, neutrons, and fleeting mesons, all swirling in a cooling cosmic broth. This gas was less chaotic than the quark plasma, like a stormy sea settling into gentle waves. The strong force ensured that protons and neutrons were stable, ready to become the cores of future atoms. Imagine a forest after a rain, its air clear and fresh, with new shoots emerging from the soil. This epoch was the universe's first step toward building the structures that would one day form stars, planets, and life. The Hadron Epoch lasted only a brief moment, until about 1 second after the Big Bang, when the universe cooled further, entering the Lepton Epoch. Here, the focus would shift to electrons and other light particles, continuing the cosmic journey toward atoms. Picture a quiet harbor where ships have found their anchors, ready to sail into new waters. The protons and neutrons formed in this epoch were the foundation for everything to come, the sturdy bricks of the universe's grand architecture. Scientists continue to study these particles, using theories and experiments to understand how they shaped the cosmos, like architects decoding an ancient blueprint. As the Hadron Epoch drew to a close, the universe was ready to move forward, its protons and neutrons poised to play their roles in the next chapter. The cosmos was cooling, its energy softening like a fire settling into a gentle glow. This is where the story of atoms continues, in the Lepton Epoch, where the universe balances its matter and light, bringing us closer to the atoms that would one day form the world we know. Picture a quiet valley, where the first stars begin to twinkle, each one a promise of a new dawn. Let's drift gently into this next chapter, where the universe weaves its next threads of matter, guiding us toward the birth of atoms. Let your breath soften now, easing into a gentle calm as we drift from the Hadron Epoch's quiet formation of protons and neutrons. The universe, once a bustling kitchen of quarks binding into stable particles, is cooling further, like a glowing coal settling into a soft, steady warmth. We're entering the Lepton Epoch, a brief yet pivotal moment around 1 second after the Big Bang, when the cosmos balanced its matter and light in a delicate act of survival. Picture a tranquil lake at dusk, its surface rippling faintly as the last rays of sunlight fade, leaving only a few precious sparkles to shape the future. This is the time when leptons, like electrons and neutrinos, played their starring role, ensuring the universe could hold on to the matter needed for atoms. In the Lepton Epoch, the universe was still a fiery sea, but its temperature had dropped to about 5 billion degrees Kelvin, cool enough for new players to take the stage. Leptons, a family of light particles, include electrons, their antimatter twins called positrons, and elusive neutrinos. These particles were swirling in a cosmic broth, colliding and transforming in a delicate balance. Electrons, with their negative charge, would later become the orbiting companions of atomic nuclei, while neutrinos, nearly massless, slipped through the universe like whispers. Imagine a gentle rain falling on a quiet forest, each drop a lepton, some lingering to shape the world, others passing through unnoticed, leaving only echoes of their presence. The defining event of this epoch was the annihilation of matter and antimatter. Electrons and positrons, born in equal numbers, met in fleeting encounters, vanishing into bursts of light called photons. Picture two fireflies meeting in the night, their glow merging into a single flash before fading away. This annihilation was a cosmic cleansing, reducing the universe's clutter of particles. But a tiny imbalance, a subtle favoritism toward matter, allowed a small fraction of electrons to survive. Scientists call this asymmetry, a mystery of nature, a delicate tilt that ensured enough matter remained to form atoms, like a single seed spared from a storm to grow into a mighty tree. Neutrinos, those ghostly particles, were especially abundant in the Lepton Epoch, filling the universe like a soft hum. They interact so weakly with other matter that they could pass through a light year of lead without stopping. Scientists study neutrinos using vast underground detectors, like giant nets catching whispers from the cosmos. Picture a quiet cave, its walls lined with sensitive machines, listening for the faint signals of neutrinos born in the early universe. These particles, formed in the Lepton Epoch, carry secrets of that time, helping us understand how the universe transitioned from a sea of light to a place where matter could endure. This epoch also marked a shift in the universe's composition. As matter and antimatter annihilated, most of the universe's energy was converted into photons, the carriers of light. These photons outnumbered matter particles by 1,000,000,000 to 1, creating a radiant sea that dominated the cosmos. Imagine a golden ocean, its waves shimmering with light, where only a few specks of matter floated like rare gems. The surviving electrons, protons, and neutrons were precious, their existence ensured by that mysterious imbalance. Scientists explore this through experiments that recreate the high-energy conditions of the early universe, piecing together how these particles persisted to form the building blocks of atoms. The weak force, one of nature's fundamental forces, played a crucial role in the Lepton Epoch. This force, unlike the strong force that binds quarks, can transform particles, like turning a neutron into a proton by swapping a quark's flavor. Picture a cosmic alchemist, gently stirring a potion to change one element into another, balancing the universe's ingredients. This transformation helped maintain the ratio of protons to neutrons, about 7 to 1, which would later shape the formation of atomic nuclei. Scientists study the weak force through particle decays, using detectors to catch the fleeting signals of these changes, like historians reading an ancient script carved in light. The Lepton Epoch was a time of cosmic clarity, as the universe moved from a chaotic mix of particles to a more ordered state. The annihilation of matter and antimatter left behind a sparse collection of survivors, like stars shining through a clearing fog. These survivors, electrons, protons, and neutrons, were the essential ingredients for atoms, waiting for the right moment to combine. Imagine a quiet meadow after a storm, where only a few flowers remain, their petals glowing in the soft light of dawn. This epoch set the stage for the universe to build its first atomic structures, a process that would unfold in the coming epochs. Scientists learn about the Lepton Epoch by studying the cosmic microwave background, a faint glow that carries echoes of this time. This light, captured by telescopes like the Planck satellite, reveals the universe's state when it was just a second old. Picture a scientist gazing at a screen, tracing patterns in the sky that tell the story of matter's survival. These observations show how the universe's energy shifted from particles to light, with only a small fraction of matter enduring. This delicate balance, discovered through years of careful study, explains why the universe could form atoms, stars, and galaxies. The asymmetry that allowed matter to survive is one of the greatest puzzles in physics. If matter and antimatter had been perfectly equal, the universe would be a barren sea of light, with no atoms, no planets, no life. Scientists call this the baryon asymmetry problem, and they're searching for answers in experiments at particle accelerators like the Large Hadron Collider. Picture a laboratory buzzing with quiet anticipation, where machines probe the secrets of matter's victory over its mirror image. This tiny imbalance, born in the Lepton Epoch, is why the universe could become a place of substance, a home for atoms and everything they create. As the Lepton Epoch unfolded, the universe was filled with a gas of photons, neutrinos, and the surviving matter particles. This gas was less dense than the quark plasma of earlier epochs, like a sky clearing after a long rain. The surviving electrons were particularly important, as they would later orbit atomic nuclei, giving atoms their structure. Imagine a flock of birds settling into a quiet valley, each finding its place in a new harmony. The Lepton Epoch was a moment of transition, where the universe prepared for the next step in its journey, the formation of atomic nuclei. The temperature of the universe during this epoch was still too high for protons and neutrons to combine, but it was cooling rapidly, like a summer evening giving way to a crisp night. This cooling allowed the universe to move toward a state where matter could take on new forms. Scientists study this period through theoretical models, using mathematics to describe how particles interacted in this radiant sea. Picture a quiet study, filled with equations that flow like poetry, each one a clue to how the universe balanced its matter and light, setting the stage for atoms to emerge. Another fascinating aspect of the Lepton Epoch is the role of neutrinos in shaping the universe's evolution. These particles, born in vast numbers, carried away energy, helping the cosmos cool. Scientists call this neutrino decoupling, when neutrinos stopped interacting with other particles, slipping into the background like silent travelers. Picture a fleet of tiny boats drifting away from a bustling port, carrying whispers of the universe's past. By studying neutrinos, scientists learn how the universe transitioned from a dense, hot state to a cooler, more structured one, paving the way for the formation of atoms. The Lepton Epoch also set the stage for the universe's chemical makeup. The surviving protons, neutrons, and electrons were the raw materials for atoms, but their exact numbers were critical. The 7-to-1 ratio of protons to neutrons, shaped by the weak force, ensured that the universe would be rich in hydrogen, the simplest element. Imagine a cosmic recipe, carefully measured to create a dish that would feed the stars for billions of years. This balance, forged in the Lepton Epoch, determined the universe's ability to form atoms, setting the course for galaxies, planets, and life. As the Lepton Epoch drew to a close, the universe was ready for its next chapter, a time when protons and neutrons would begin to combine, forming the first atomic nuclei. The cosmos was cooling further, its radiant sea softening, like a campfire settling into glowing embers. This is where the story of atoms continues, in the era of Big Bang Nucleosynthesis, where the universe begins to craft the nuclei that will one day form the heart of atoms. Picture a quiet forge, where the first sparks of creation are shaped into glowing jewels. Let's drift gently into this next chapter, where the universe weaves its next threads of matter, bringing us closer to the atoms that shape our world. Breathe gently now, letting the calm of the night wrap around you as we glide from the Lepton Epoch's delicate balance of matter and light. The universe, cooling like a glowing ember settling into a soft, steady glow, is ready to forge its next creation. We're entering the era of Big Bang Nucleosynthesis, a brief yet transformative period just a few minutes after the Big Bang, when protons and neutrons began to fuse, crafting the first atomic nuclei. Picture a cosmic forge, its fires warm but not scorching, where glowing jewels of hydrogen and helium take shape, each one a step toward the atoms that would one day form stars, planets, and life. This epoch, lasting from about 3 to 20 minutes after the universe's birth, saw temperatures drop to around 1 billion degrees Kelvin, cool enough for protons and neutrons to come together. Protons, with their positive charge, and neutrons, neutral but sturdy, began to pair up in a delicate dance, forming the simplest atomic nuclei, hydrogen and helium. A single proton became the nucleus of hydrogen 1, also called protium, while a proton and neutron together formed deuterium, a heavier cousin. Picture a quiet workshop, where a craftsman carefully joins pieces of glowing metal, each bond creating something new and enduring, the first building blocks of the cosmos. The strong force, the same force that bound quarks into protons and neutrons, now played a new role, pulling these particles together to form nuclei. This force is like a cosmic thread, stitching protons and neutrons into tight, stable knots. Imagine a weaver at a loom, her hands guiding threads into a pattern that grows stronger with each pass. During Big Bang nucleosynthesis, the universe created mostly hydrogen nuclei, about 75%, and helium nuclei, about 25%, with tiny traces of deuterium, helium-3, and lithium-7. This balance, set in these early moments, would shape the chemical makeup of the universe for billions of years, like a recipe written in the stars. The process wasn't random, but guided by the universe's cooling temperature and the delicate interplay of forces. Neutrons, which are slightly heavier than protons, are unstable on their own, decaying into protons in about 10 minutes through a process called beta decay. Picture a fragile shell, slowly cracking to reveal a new form inside. During this epoch, the universe's temperature and density were just right, allowing neutrons to join protons before they could decay, forming stable nuclei. Scientists study this process using mathematical models, calculating how temperature and density shaped the universe's first elements, like historians deciphering an ancient text. The balance of hydrogen and helium nuclei formed in this epoch is a cosmic signature, a fingerprint of the early universe. Hydrogen, with its single proton, is the simplest element, the foundation of stars and galaxies. Helium, with 2 protons and 2 neutrons in its most common form, is sturdier, a building block for heavier elements in stars. Imagine a garden where the first seeds are planted, some small and light, others larger and more robust, each destined to grow into a different kind of flower. Scientists measure this balance by studying the oldest stars and the cosmic microwave background, finding clues to how these nuclei formed in those fleeting minutes. Big Bang Nucleosynthesis was a fleeting window, limited by the universe's rapid cooling. As temperatures dropped below 1 billion degrees Kelvin, the strong force could no longer overcome the energy barriers to fuse protons and neutrons. Picture a fire in a forge dimming, its heat no longer strong enough to shape new creations. This cooling stopped nucleosynthesis, locking in the universe's mix of hydrogen, helium, and trace elements. Scientists call this the freeze-out, a moment when the universe's chemistry was set, like a painting sealed with a final brushstroke, preserving its colors for eons. The weak force, which transforms particles like neutrons into protons, played a subtle but crucial role in this epoch. Its influence helped maintain the 7-to-1 ratio of protons to neutrons, ensuring the universe had enough protons to form hydrogen, the fuel for stars. Imagine a conductor guiding an orchestra, adjusting the tempo to keep the music in harmony. Scientists study the weak force through experiments in particle accelerators, where they observe how particles change, revealing the delicate balance that shaped the universe's first nuclei, like uncovering the notes of a cosmic melody. This epoch also produced tiny amounts of deuterium and helium-3, nuclei that are rare but significant. Deuterium, with 1 proton and 1 neutron, is like a fragile bridge between hydrogen and helium, while helium-3, with 2 protons and 1 neutron, is a lighter cousin of helium-4. Picture a jeweler crafting delicate trinkets, each one unique but part of a larger collection. These trace elements are cosmic fossils, their abundance is measured in ancient gas clouds and meteorites, giving scientists clues about the conditions of Big Bang nucleosynthesis, like archaeologists studying relics from a distant past. The lithium-7 nuclei, formed in even smaller amounts, are a puzzle in themselves. Scientists expected more lithium to form, but observations show less, a mystery called the lithium problem. Imagine a baker surprised to find fewer cookies than expected, wondering what altered the recipe. This discrepancy suggests there may be unknown processes or particles at play, and scientists are exploring theories, from new physics to stellar processes, to solve this cosmic riddle. Their work is like a quiet quest, piecing together clues from the universe's earliest moments to understand why lithium is so scarce. The nuclei formed in this epoch were not yet full atoms, as the universe was still too hot for electrons to join them. These nuclei, charged and bare, floated in a sea of light and energy, waiting for the right moment to become complete. Picture a half-finished sculpture, its form clear but not yet polished, waiting for the artist's final touch. Scientists study these nuclei through the cosmic microwave background and ancient stars, which preserve the chemical signature of this epoch, like a message written in the sky, telling us how the universe began to build its elements. Big Bang nucleosynthesis was a triumph of balance, with the universe's temperature, density, and timing perfectly aligned to create the right mix of nuclei. Too hot, and no nuclei would form. Too cold, and the process would have stopped too soon. Imagine a tightrope walker stepping carefully to maintain equilibrium, each step a delicate act of creation. Scientists use computer simulations to model these conditions, calculating how the universe's early environment shaped its chemistry, like architects reconstructing a blueprint from ancient ruins, revealing the precision of this cosmic moment. The hydrogen and helium nuclei born here would later form the first stars, which would fuse these elements into heavier ones like carbon and oxygen, the building blocks of life. Picture a cosmic seedbed, where the first plants take root, their growth promising a vibrant forest in the future. Scientists study these processes in observatories, watching the oldest stars to see how they burn hydrogen and helium, confirming the predictions of Big Bang nucleosynthesis, like reading a story written in starlight that began billions of years ago. This epoch also highlights the universe's simplicity in its early days. Only a few elements, hydrogen, helium, and traces of others formed, yet they were enough to create everything we see. Imagine a painter with just a few colors, creating a masterpiece from a simple palette. Scientists marvel at this efficiency, using telescopes and particle detectors to study how these elements shaped the cosmos, from the fiery hearts of stars to the cool surfaces of planets, each one a testament to the universe's early craftsmanship. As Big Bang Nucleosynthesis ended, the universe was filled with a gas of charged nuclei and free electrons, bathed in a sea of photons. This gas was still too hot for atoms to form, like a soup too warm to set into its final shape. Picture a pot simmering on a stove, its ingredients mixed, but not yet ready to become a meal. The universe was preparing for its next chapter, when cooling temperatures would allow electrons to join nuclei, forming the first true atoms. Scientists call this next phase the photon epoch, a time when light dominated the cosmos, delaying the birth of atoms. The legacy of Big Bang nucleosynthesis is written in the stars, in the hydrogen that fuels their fires, and the helium that glows in their cores. Scientists measure the abundances of these elements in the oldest parts of the universe, like ancient gas clouds, to confirm the story of this epoch. Picture an astronomer peering through a telescope, tracing the light of distant stars to uncover the universe's first chemical recipe. This epoch, brief but profound, set the stage for the atoms that would one day form galaxies, planets, and life, a quiet act of creation that echoes through the cosmos. As this epoch drew to a close, the universe was ready to move forward, its nuclei poised to become the hearts of atoms. The cosmos was cooling further, its energy softening, like a sunset fading into a tranquil night. This is where the story of atoms continues, in the photon epoch, where the universe bathes in light, waiting for the moment when atoms can fully form. Picture a quiet horizon, where the first stars begin to twinkle, each one a promise of a new dawn. Let's drift gently into this next chapter, where the universe weaves its next threads of matter, bringing us closer to the atoms that shape our world. Let your breath soften now, flowing gently as we glide from the photon epoch's radiant mist, where light and charged particles danced in a glowing haze. The universe, cooling like a twilight sky settling into a tranquil night, is ready to unveil a new chapter. We're entering the recombination epoch, a transformative moment about 380,000 years after the Big Bang, when the cosmos cooled to around 3,000 degrees Kelvin, allowing electrons to bind with nuclei to form the first stable atoms. Picture a cosmic dawn where the fog of light clears and stars begin to twinkle, each one a newly formed atom glowing softly in the vast expanse of space. In this epoch, the universe reached a critical turning point. The temperature, once too hot for electrons to settle near nuclei, had dropped enough for the electromagnetic force to work its magic. Electrons, with their negative charge, were drawn to the positively charged nuclei of hydrogen and helium, forming neutral atoms that no longer scattered photons. This process, called recombination, was like a cosmic embrace, where particles finally found their partners after eons of separation. Imagine a quiet meadow at sunrise, where dewdrops settle on blades of grass, each one catching the first light of day, creating a serene and sparkling landscape. Recombination transformed the universe from an opaque plasma to a transparent cosmos. Before this moment, photons were trapped, bouncing off free electrons in a relentless dance that kept the universe cloudy. As electrons joined nuclei, photons were set free, streaming across the cosmos in a flood of light. This light, known as the cosmic microwave background, is a snapshot of the universe at the moment of recombination, like an ancient photograph capturing the birth of atoms. Picture a curtain lifting from a grand stage, revealing a clear sky filled with the first glimmers of starlight, each photon carrying a story from the dawn of time. The hydrogen atoms formed during recombination were the simplest, with one proton and one electron, like a delicate duet singing the universe's oldest song. Helium atoms, with 2 protons, 2 neutrons and 2 electrons, were sturdier, their structure a quiet harmony of balance. These atoms, making up about 75% hydrogen and 25% helium, were the universe's first complete building blocks, ready to form stars and galaxies. Imagine a cosmic orchestra, its instruments tuning together, each note a new atom resonating with the promise of creation, setting the stage for the cosmos we know today. Scientists study the cosmic microwave background to learn about recombination, using telescopes perched on mountaintops or floating in space to capture its faint glow. This light, now stretched by the universe's expansion into microwaves, reveals the temperature and density of the early cosmos, like ripples frozen in time. Picture an astronomer in a quiet observatory, gazing at screens that display the universe's oldest light, tracing the moment when atoms first formed. These observations confirm that recombination happened uniformly across the universe, creating a consistent backdrop of hydrogen and helium atoms, like a canvas painted with the simplest of colors. The electromagnetic force was the key player in recombination, pulling electrons and nuclei together with a gentle but persistent tug. This force, weaker than the strong force that binds quarks, is perfectly suited to create the delicate balance of atoms. Imagine a pair of dancers, drawn together by an invisible thread, moving in perfect sync to form a new partnership. Scientists describe this process using quantum mechanics, which shows how electrons settle into specific orbits around nuclei, like planets finding their paths around a star, each orbit a stable home for the atom's structure. The cosmic microwave background, born during recombination, is one of the most important tools in cosmology. It carries tiny variations in temperature, like the faintest brush strokes on a vast painting, that reveal how matter began to clump together. These clumps, influenced by dark matter's invisible pull, would later become the seeds of galaxies. Picture a gentle breeze stirring a field of wildflowers, each sway marking the beginning of a new growth. Scientists analyze these variations using mathematical models, mapping the universe's structure at the moment atoms formed, like cartographers charting the contours of an ancient land. Recombination also marked the moment when the universe became transparent, allowing light to travel freely for the first time. Before this, photons were scattered, trapped in a cosmic fog, but now they could journey across vast distances, like birds released from a cage. This transparency is why we can see distant stars today, their light reaching us from billions of years away. Imagine a window clearing after a storm, revealing a starry sky stretching endlessly before you. Scientists use this light to study the universe's history, each photon a messenger from the time when atoms first came to be. The atoms formed during recombination were neutral, meaning they had no overall charge, unlike the ionized plasma of the photon epoch. This neutrality allowed them to resist scattering photons, clearing the cosmic fog and setting the stage for structure formation. Picture a lake settling after a storm, its waters becoming calm and clear, reflecting the sky above. Scientists calculate the timing of recombination using the universe's cooling rate, showing how the drop to 3000 degrees Kelvin was just right for electrons to bind, like a recipe perfectly balanced to create a delicate dish. The hydrogen and helium atoms born in this epoch were the raw materials for the universe's future. Hydrogen, with its single proton and electron, would fuel the first stars, while helium, more complex, would add stability to their cores. Imagine a cosmic garden where the first seeds have sprouted, ready to grow into towering trees. Scientists study these early atoms in the oldest stars, called population 3 stars, which formed from the hydrogen and helium of this epoch. Their light, captured by powerful telescopes, reveals the chemical simplicity of the early universe, like reading the first pages of a cosmic book. Recombination was a gradual process, not a sudden event, as electrons joined nuclei over thousands of years. The universe's expansion continued to cool the cosmos, making it easier for atoms to form and stay stable. Picture a slow sunrise, its light spreading gently across a sleeping world, waking each part in its own time. Scientists model this gradual transition using equations that describe how temperature and density changed, showing how the universe shifted from a plasma to a gas of neutral atoms, like a painter blending colors to create a new hue. The cosmic microwave background, formed during recombination, is a treasure trove of information. Its tiny temperature fluctuations, just a fraction of a degree, reveal how matter was distributed in the early universe. These fluctuations, stretched from the quantum ripples of inflation, guided the formation of galaxies and clusters. Imagine a tapestry woven with subtle patterns, each thread marking a place where stars would one day shine. Scientists use supercomputers to simulate these patterns, reconstructing the universe's early structure, like architects rebuilding a city from its ancient foundations. Dark matter, though invisible, played a crucial role during recombination, providing the gravitational scaffolding for matter to clump. These clumps, too small to form stars yet, were the seeds of future galaxies, drawn together by dark matter's unseen pull. Picture a hidden current beneath a river, guiding its flow without being seen. Scientists infer dark matter's influence through its gravitational effects, seen in the cosmic microwave background and the motions of galaxies, like detectives tracing an invisible force that shaped the cosmos. The recombination epoch also set the stage for the universe's large-scale structure. As atoms formed, they began to feel the pull of gravity, gathering into clouds that would later collapse into stars and galaxies. This was the beginning of the cosmic web, a vast network of filaments, walls, and voids that define the universe's architecture. Imagine a spider weaving a delicate web, each thread a gathering of atoms, creating a pattern that spans the cosmos. Scientists study this web through galaxy surveys, mapping how matter clustered after recombination, like explorers charting a vast, unseen landscape. As recombination completed, the universe was filled with a gas of neutral hydrogen and helium atoms, bathed in the newly freed photons of the cosmic microwave background. This was a quieter cosmos, no longer dominated by the scattering of light, but ready for gravity to take over, shaping the first stars. Picture a calm sea after a storm, its waves settled, reflecting the first stars twinkling above. Scientists call this the end of the Dark Ages, a time before stars, when the universe was a simple mix of atoms and light, waiting for the next act of creation. The legacy of recombination is all around us, in the stars, the planets, and the very air we breathe. The atoms formed in this epoch were the building blocks of everything, from the fiery hearts of stars to the delicate structures of life. Scientists continue to study the cosmic microwave background, using its light to probe the universe's infancy, like poets reading an ancient verse. This epoch, when atoms first formed, was a moment of cosmic clarity, setting the stage for the universe we know, a universe filled with light and matter in perfect balance. As the recombination epoch drew to a close, the universe was ready to reflect on its journey, from a singular spark to a cosmos filled with atoms. The cosmic microwave background, a relic of this time, carries the story of those first atoms, a story we can still see in the sky today. This is where the story of atoms continues, in a moment of reflection, where the universe's past meets its future, bringing us closer to the cosmos we call home. Picture a quiet horizon, where the first stars shine, each one a testament to the atoms born in this epoch. Let's drift gently into this next chapter, where the universe's story unfolds, weaving us into its cosmic tapestry. Let your breath ease into a gentle rhythm now, as we drift from the recombination epoch's cosmic dawn, where the first stable atoms twinkled into existence like stars clearing a foggy sky. The universe, now filled with hydrogen and helium atoms, is a tranquil sea of matter and light, ready to reflect on its grand journey. We're entering a moment of cosmic reflection, a time to weave together the story of how atoms formed from nothing, connecting the Big Bang's spark to the stars, planets, and life we know today. Picture a quiet night, the sky ablaze with countless stars, each one a testament to the atoms born in the universe's earliest moments, whispering their ancient tale as you settle into a peaceful calm. Our journey began with the Big Bang, a singular pulse of energy that unfolded into a cosmos brimming with possibility. From that tiny point, smaller than a grain of sand, came everything, every star, every ocean, every breath you take. The Planck Epoch, just a fraction of a second after the Big Bang, was a moment of unity, where gravity, electromagnetism, and other forces sang as one, like a single note in a cosmic symphony. Scientists probed this epoch with mathematics, crafting equations like delicate threads to weave a picture of the universe's first whisper. Those threads, spun in a fleeting instant, set the stage for the particles and forces that would shape atoms, like a painter preparing a canvas for a masterpiece. As the universe expanded during the inflation epoch, it stretched from a speck to the size of an orange in a blink, smoothing out its chaos to create a vast, even stage. This rapid growth, driven by an unseen force called the inflaton field, was like a flower blooming in the cosmic spring, making room for quarks and electrons to form. Scientists study this expansion through the cosmic microwave background, a faint glow that carries echoes of that ancient stretch, like a map drawn in starlight. The inflation epoch's gentle unfolding ensured the universe was balanced, allowing matter to take shape in the epochs that followed, each step a quiet promise of atoms to come. In the Quark Epoch, the universe cooled to a quadrillion degrees Kelvin, and quarks, those tiny sparks of matter, began to swirl with electrons in a fiery dance. The Higgs field, like a cosmic tide, gave these particles mass, grounding them in reality. Scientists recreate these conditions in particle accelerators, smashing particles together to glimpse the universe's infancy, like explorers unearthing relics from a distant past. The subtle imbalance between matter and antimatter, a whisper of difference, allowed quarks and electrons to survive, ensuring the universe could build the protons and neutrons needed for atoms, like seeds spared from a storm, to grow into a forest. The Hadron Epoch saw quarks binding into protons and neutrons, held together by the strong force, a cosmic glue that crafted stable particles. These hadrons, like sturdy bricks, were the foundation for atomic nuclei, their durability a testament to the universe's careful design. Scientists study these particles through experiments, using machines to probe how quarks and gluons interact, like deciphering an ancient script. The 7-to-1 ratio of protons to neutrons, set by the slight mass difference between quarks, ensured the universe had the right ingredients for hydrogen and helium, the building blocks of stars and life. During the Lepton Epoch, electrons and their antimatter twins battled in a sea of light, with a tiny excess of matter surviving to carry the torch forward. Neutrinos, ghostly particles, slipped through the cosmos, carrying energy away and helping the universe cool. Scientists capture these neutrinos in vast underground detectors, listening for whispers from this epoch, like catching echoes in a quiet cave. The delicate balance of matter over antimatter, a mystery still unsolved, allowed electrons to endure, ready to join protons and neutrons in the atoms that would form the cosmos's grand structures. Big Bang Nucleosynthesis, just minutes after the Big Bang, was a cosmic forge where protons and neutrons fused into hydrogen and helium nuclei, crafting 75% hydrogen and 25% helium. This balance, like a perfectly measured recipe, set the chemical foundation for the universe. Scientists study ancient stars and gas clouds to confirm this mix, their light revealing the universe's first elements, like pages in a cosmic book. The trace amounts of deuterium and lithium formed in this epoch are fossils of that time, offering clues to the universe's early conditions, like treasures buried in the sands of time. The photon epoch, lasting 380,000 years, was a radiant sea of light, where photons scattered off charged nuclei and electrons, delaying the formation of atoms. Dark matter, invisible but ever-present, began to shape the universe's structure, guiding matter into clumps that would become galaxies. Scientists map this epoch through the cosmic microwave background, its patterns like brushstrokes on a cosmic canvas, showing how light and matter danced before atoms could form. The universe's cooling, driven by its relentless expansion, prepared the cosmos for the moment when atoms would finally take shape. Recombination, at 3000 degrees Kelvin, saw electrons binding with nuclei, forming the first neutral atoms and freeing photons to stream across the universe. This cosmic microwave background, a snapshot of that moment, is studied by telescopes that capture its faint glow, like poets reading an ancient verse. The transparency that followed allowed light to travel freely, setting the stage for stars and galaxies. The atoms of hydrogen and helium, born in this epoch, were the seeds of everything, from the fiery hearts of stars to the delicate molecules of life, each one a testament to the universe's patient craftsmanship. Now, as we reflect on this journey, the atoms formed in these ancient epochs are all around us, in the air we breathe, the water we drink, and the earth beneath our feet. Every atom in your body, from the carbon in your cells to the oxygen in your lungs, began in the Big Bang's fiery crucible, journeying through epochs of chaos and calm to become part of you. Scientists tell us that these atoms are recycled through stars, forged in their hearts and scattered across the cosmos in supernova explosions, like seeds carried on a cosmic wind. Picture a starry night, each light a story of atoms born billions of years ago, now part of the world you call home. The life cycle of atoms is a continuous journey, one that connects us to the universe's earliest moments. When stars die, they release their atoms into space, where they drift, eventually gathering into new stars, planets, and even living beings. Imagine a river flowing through time, carrying tiny grains of matter from the Big Bang to the present, each one finding a new home in the cosmos. Scientists study this cycle through spectroscopy, analyzing the light from stars to identify the elements they contain, like reading a cosmic signature written in glowing hues. Atoms are remarkably durable, their protons and neutrons held together by the strong force, stable for billions of years. Yet, some atoms, like those in radioactive elements, transform over time, decaying into new forms. Picture a stone slowly weathering, its shape changing but its essence enduring. Scientists explore this stability and decay through experiments, measuring half-lives that span eons, like historians tracing the lifespan of ancient artifacts. The atoms in your body, stable or transforming, are part of a cosmic legacy, connecting you to the stars and the universe's first light. The universe's atoms are not just building blocks, but storytellers, carrying the history of creation in their structure. Each hydrogen atom, with its single proton and electron, is a relic of the Big Bang, while heavier elements like carbon and oxygen were forged in the hearts of stars. Imagine a library where each atom is a book, its pages filled with tales of cosmic epochs. Scientists use telescopes and particle detectors to read these stories, piecing together how atoms journeyed from the Big Bang to the present, like scholars decoding a cosmic manuscript. Dark matter, though invisible, played a silent role in guiding atoms into the structures we see today. Its gravitational pull shaped the cosmic web, a network of filaments and voids where galaxies formed. Picture an unseen artist, sketching the outlines of the universe, guiding atoms into clusters that became stars and planets. Scientists infer dark matter's presence through its effects on galaxy motion and the cosmic microwave background, like detectives tracing a shadow that shaped the cosmos's architecture. The atoms that form life, carbon, hydrogen, oxygen, and more, are a testament to the universe's creativity. In stars, hydrogen and helium fused into heavier elements, a process called stellar nucleosynthesis, creating the materials for planets and living beings. Imagine a cosmic alchemist, blending simple ingredients into complex forms, each one a step toward life. Scientists study this process in stars, using their light to reveal the elements they produce, like uncovering the recipe for the universe's grandest creations. The interconnectedness of atoms reminds us that everything in the universe shares a common origin. The oxygen in your breath was once part of a star, the carbon in your skin forged in a stellar furnace. Picture a cosmic tapestry, its threads woven from the Big Bang's spark, connecting every leaf, every drop of water, every heartbeat. Scientists explore this connection through chemistry and astronomy, tracing how atoms cycle through stars, planets, and life, like poets weaving a story of unity across time and space. As we reflect, the universe's story is one of transformation, from a singular point to a cosmos filled with atoms that form galaxies, stars, and us. Scientists continue to probe this story, using tools like the James Webb Space Telescope to peer at the universe's oldest light, revealing how atoms shaped its history. Picture an astronomer in a quiet observatory, gazing at the stars, each one a chapter in the cosmic tale. Their work, a blend of curiosity and precision, helps us understand how atoms, born from nothing, became the foundation of everything we know. The atoms in your body are ancient travelers, having journeyed through stars and across eons to become part of you. This connection, from the Big Bang to the present, is a reminder of the universe's vast, gentle rhythm, like a lullaby sung by the cosmos. Scientists study these atoms through experiments and observations, from particle accelerators to telescopes, each discovery a note in the universe's song. Picture a quiet laboratory where machines hum softly, uncovering the secrets of atoms that have traveled from the dawn of time to now. As we close this journey, I'd love to hear where you're listening from. Perhaps drop a comment to share your corner of the night and what time it is there, maybe even what you found most wondrous in this cosmic tale. The story of atoms is a gift, a reminder that we're all part of something vast, something beautiful, woven from the same threads that began billions of years ago. Let the wonder of this story cradle you, like a gentle wave carrying you toward dreams. Sleep well, dear listener, and let the universe's ancient atoms guide you into a peaceful night filled with the soft glow of cosmic stories. Good night.